So is it people going to the institute nowadays or only few of you?
Few. We're restarting.
Yeah, okay. I haven't been back to IFIC yet.
Is it closed, IFIC?
It's not closed, but they ask theorists not to come unless it's strictly necessary. So they essentially said that the least relevant, necessary people, you know, we should stay home unless there is any important issue. Yeah,
it's similar here.
Yeah. So yeah, I don't know about other colleagues of the department, but I think nobody's really going to their office. Only the experimentalist. Experimentalist. Yeah.
And how about classes?
Well, classes, since this is now summer, I think right now there is not the problem, but before they've been teaching online. In the last month, they've been teaching online. There is this application, I think, that most people is using, and apparently was working pretty well. Yeah, but to be honest, I don't really know because I don't have to teach myself. So I don't know what is the idea for instance, for September, you know, for next semester. Yeah. It looks to me they may want to go. Well, it's not clear. Sorry. Yeah, I was going to say they may want to go online, but it's not clear because maybe they just go to normal, you know, physically attending classes. Not sure. Do you see already the PDF, the screen?
Yes.
Okay, yes. Very good.
If you are ready, Daniel, maybe we can start, so we are on time.
Yeah, happy to go for it.
Okay. So next we have Daniel Figueroa, who will lecture for the third time on gravitational waves. Thank you.
Okay, well, welcome back, everybody. This is the third and last lecture on the topic on gravitational wave backgrounds from the early universe, so cosmological backgrounds. What we've seen so far, if you recall, on the first lecture was the definition on gravitational waves. And then a couple of days ago, we were dealing with the production and somehow propagation of gravitational waves from inflation and from reheating. Today, we are going to cover these last two highlighted topics, gravitational waves from phase transitions and from cosmic defects. And the first observation we can make is actually that when we talk about phase transitions, this actually can be connected to reheating or preheating, because it is possible to end inflation, to finish inflation with a phase transition, something that I mentioned in passing by in the lecture 2 days ago, but we will see in detail today. So if you remember, there is this picture of everything we've been seeing, and we stopped at preheating last time. We had covered a scalar preheating, so preheating non-perturbative effects with scalar fields, which were leading to a large production of gravitational waves, but always at high frequency. So let us ask ourselves what happens now if we make more complicated, but yet more realistic the scenario, for instance, having gauge fields. And we are going to think of embedding of a gauge framework into the scenarios of hybrid preheating that we were discussing 2 days ago, because as I will highlight and emphasize now, they correspond actually to a phase transition, the preheating in these scenarios, okay? So let us recall what these scenarios are about. So we have like two fields involved in the game. On the one hand, there is an inflaton, which is a singlet. And on the other hand, there is a symmetry breaking field. Let me call it generically a Higgs, whether this is the Higgs of the standard model or not. It's up to you. It depends on the scenario, I mean, but It's some field with a Mexican hat kind of potential, which is coupled directly to the inflaton. So for instance, here we are providing a mass to the inflaton, or you could give some potential if you want. And then there is this coupling between the Higgs-like field and the inflaton. At the same time, the Higgs has its own self-interacting coupling, and it has a non-vanishing vacuum expectation value, which will be the end state after the phase transition, as we will see in a moment. And we also define a critical value, which is given by this mass of the Higgs in the true BEV divided by the coupling between the inflaton and the Higgs. So essentially, put it in a more pictorial way, the multi-field potential of this scenario looks as follows. There is a direction for the inflaton and a direction for the Higgs. Be aware that here I'm plotting one direction for the Higgs, but this could be a scalar multiplet, so it could have several components in its own internal space, okay? Like for instance, the doublet of the Higgs in the standard model that would have 4 components. Now, during inflation, the inflaton is slowly rolling along this valley. Eventually, it hits this critical value that we defined before, and this flips the sign of the effective mass of the Higgs such that it becomes tachyonic. And if you remember, what we said is when this happens, of course, you trigger preheating because this tachyonicness corresponds to growth of the amplitude of the Higgs fluctuations. But from another point of view, this is the same as a phase transition, which is what I was saying before. Why is that? Because while the inflaton was coming along its path in this valley, the effective potential of the Higgs had a single minimum, okay, and had a big mass, if you want, the Higgs. So it was stuck at the minimum of its potential with some dispersion. When it crosses, however, the critical point, the inflaton, what we see here is that the Higgs potential flattens out. And then as soon as the inflaton moves slightly forward, critical value, then we see that the Higgs potential develops to minima. I insist this is one direction. If it was multi-component Higgs field, this would be a vacuum manifold, okay, in that internal space. But okay, in this picture, for simplicity, in this Mexican hat potential one-dimensional view, we see 2 minima, okay, at minus 1 BeV plus another BeV. So this is the prototype of symmetry breaking potential for a phase transition, no? Because we are going to change from a situation in which there was explicitly one symmetry respected by vacuum, and then suddenly we'll see that vacuum does not respect the symmetry anymore because it can take a non-vanishing vacuum expectation value. And this is precisely what happens, okay? This is a phase transition. And in this case, the order parameter, which is the amplitude of the Higgs of the multi-component Higgs, it's rolling, if you want, very fast, exponentially fast, actually, towards its true minimum through the tachyonic instability triggered by the inflaton crossing this critical value. Okay, so now we are going to study this scenario from the point of view of this being a phase transition. And taking into account that naturally, if you have a Higgs field, this is a charge scalar, which is going to be naturally coupled to gauge fields. Okay, so for simplicity, I'm going to consider a U1 sector. Let it, if had this been the Higgs of the standard model, then it should have been the SU2 cross U1 sector, etc. Okay, but for simplicity, let me stick to U1 sector, since we are not even identifying what is this Higgs field.
Excuse me, Daniel. There's a question from Anupam about the previous slide. The question is critical value of phi critical.
Yes.
You put it by hand?
No, I don't put it by hand. This is given by this parameter. So for a given choice of your self-coupling of the Higgs, a given choice of the vacuum expectation value of the Higgs, and a given choice of the coupling between the Higgs and the inflaton, then there is this critical value. So if you write down the interaction G squared, Higgs squared, inflaton squared, then there will be always this critical value. Okay, so it's not something I put by hand. Is that here you have the negative value from the tachyonicness, intrinsic tachyonicness of the Mexican hat potential, and here you have the quadratic part from the interaction. Okay, which I'm just writing in a convenient way like this, but it's it brings up naturally this critical value. Okay, given your choice of initial parameters, of course. So as I said, this triggers a phase transition. And we do have gauge fields in the game in any realistic setup, no? Because you should gauge this setup. And essentially, this implies that now we're going to study this idea of the phase transition, knowing that there are gauge fields into the game. And since we know that the Higgs field is going to be excited through the tachyonic instability, this also means that as soon as we excite the Higgs, we are also going to excite in a significant manner the gauge fields, okay, since they are directly coupled to the Higgs through the covariant derivative. All right, so essentially, we need to study this in the lattice. I'm not going to show you the lattice equations of motion because most of you probably are not familiar with these techniques when there are gauge fields, but I'm going to show you the equivalent of the equations of motion in the continuum, okay? We just need to discretize this in the lattice when we do the actual operation, but let me discuss them from the point of view of the continuum. So essentially, if we want to discuss the dynamics of this phase transition, on the one hand, we have to follow the dynamics of the charge scalar, of the charge Higgs, with its covariant derivatives here, coupled to the gauge fields. We also have to follow the dynamics of the singlet, of the inflaton, and then we have to follow the dynamics of the gauge fields. So I'm just writing down here the standard equations, okay, for the scalar electrodynamics. And at the same time, we are going to follow, because of course, remember what we are interested here is to understand what is the production of gravitational waves. We're going to follow the wave equation of the tensor perturbations as sourced by the transverse stressless part of the new anisotropic stress, which in this case is not only formed by gradients of the scalars in the game, in this case the inflaton, but also you see not gradients but covariant gradients of the charge scalar of the Higgs, and then also gauge invariant configuration of magnetic and electric fields. Okay, so we have multiple source terms, which therefore will give rise also to interference. Okay, and now here I'm highlighting that this is these are new terms compared to what we had seen so far before, no? And this is the covariant term, magnetic and electric terms. So how does it look? Once I plug in this in the computer in a simulation and we run, the simulation, we get some output. So how does it look, the phase transition? Well, this is a three-dimensional box of the distribution of the amplitude of the Higgs. So I'm plotting with a color coding here, which goes from black to red whitish, from 0 to some non-zero value, the amplitude of the Higgs in certain regions in space. And what you see is that the tachyonic instability of the Higgs is manifested here in real space by the nucleation of bubbles with the amplitude of the Higgs inside this configuration, inside these bubbles, growing. So that in one snapshot, it has whatever value compared to the true BEV here, of the order 10 to minus 3, for instance, here. In the next one, this has grown an order of magnitude compared to the previous one, if you look at the numbers. So the bubbles are better defined. The Higgs BEV is rolling faster and faster towards the true vacuum expectation value. And at the same time, just because this minimizes energy, the walls of the bubbles are going to expand. And eventually, they are going to reach a size in which they are going to collide with each other. Okay, so this basic picture of the phase transition. However, notice that when they collide, as represented here in the final snapshot, we actually do see in the middle of the bubble some kind of a yellowish color. I, of course, don't know if you can really appreciate it because maybe the color coding here is not the best, but essentially we are seeing some regions of a space where there is in between the bubbles some very small values of the Higgs instead of very large values. So what's going on? Maybe in order to understand this, we can look at the distribution of the energy density of the magnetic field of the problem. So initially it's pretty random, but as time goes by, it grows its amplitude significantly, many orders of magnitude from here to there. And then we see that what we are developing is somehow very elongated configurations, so elongated that here they look like worms and they are very well defined, no, the shape of them. And actually what's going on is that actually we are producing cosmic strings. So these are a type of topological defects, and I will cover this in the second half of this lecture. So for the time being, we are going to ignore it, but just keep in mind that because there is a phase transition, if some conditions are met, and luckily here some conditions, those conditions are met, you can produce cosmic defects. In this case, cosmic strings. Okay? Now, forgetting about this business of cosmic strings, just focusing on the idea that we are exciting the Higgs field through the tachyonic instability. So there is a spectrum for the fluctuations of the Higgs, represented here by K3 times the Higgs K mode square. Typically, there is a middle peak due to the tachyonic instability, and maybe due to other diffusion effects that I haven't really discussed, you may or may not have this other infrared peak. Maybe we're going to forget mostly about this infrared peak, just focus on the fact that there is a middle peak due to tachyonic effects. And at the same time, the gauge fields, for instance, their magnetic field spectra, energy density spectra, they have their own spectrum, which is on peak. And you see here I'm isolating this spectrum of the energy density of magnetic field. And the position of this peak is actually located depending on the gauge coupling. In particular, since I'm measuring momenta here normalized to the Higgs mass in the TrueBev, essentially what matters here is the ratio of the gauge coupling of the fields to the self coupling of the Higgs. So the bigger this ratio, the more into the UV is displaced the position of the peak of the gauge fields, simply because they have a larger mass through the Higgs mechanism. So altogether, there is already quite a large number of parameters in this abelian Higgs scenario. And maybe the only thing I really want to highlight is that the gauge fields, they follow their own spectra, their distribution, if you want, of the modes of the gauge fields. And what controls the location of the maximum amplitude is simply the ratio of the vector mass of the gauge field mass to the Higgs mass, which is nothing else but the ratio of the gauge coupling of the gauge fields to the Higgs divided by the self coupling of the Higgs itself. Okay. Very good. So now I show you how we really built up in a simulation the gravitational waves spectrum in time. Okay, so before I was showing you the spectra of matter, now I show you what comes out from the simulation in terms of the fraction of gravitational wave energy density compared to the total one versus momentum or versus frequency. And of course, what you see is that either you have a spectra like the red one, okay, this is the spectrum of gravitational waves, where there is maybe a single peak. This is the case whenever the gauge coupling compared to the self-coupling of the Higgs are of the same order. If they are of the same order, the peak from the gauge fields is not separated, so I produce a single peak in the gravitational wave spectrum. On the opposite case, when I separate them enough, say an order of magnitude, so gauge coupling to the square root of self-coupling of the Higgs is 10, you see, since I produce a gauge field peak here and I produce a scalar peak here of the Higgs, now in the spectrum of gravitational waves, I actually have two peaks. One coming from the tachyonic instability of the Higgs, another coming from the excitation of the gauge fields here, quite separated. Okay, and you see, I can modulate, I can really tune this effect by playing around with the relative size of the gauge coupling compared to the self-coupling of the Higgs, from 10 to 7.5, 5, 2.5, 1. So I can really make it to have two peaks or one peak. So final spectra after the fields relax looks something like that in these scenarios. You typically have a middle peak. Then you do have a second peak on the more UV scales, typically for larger gauge couplings than the square root of the Higgs self-coupling. And perhaps you may have, with some power, an infrared peak or not. This depends on other details I haven't discussed. So these spectra are very characteristic of these scenarios because, first of all, there are several peaks. And secondly, this implies that if we could measure them, we could literally do this idea that I was also bringing up collaterally a couple of days ago, particle physics spectroscopy, since the location of this middle peak depends on the Higgs mass, which depends on its own self-interactions, whereas the location of this peak depends on the strength of the coupling of the gauge fields to the Higgs itself. So essentially, if we were capable of measuring background of this kind, we actually could do a spectroscopy of particle physics in a similar sense, if you want, to what we do in colliders. No? So very good. The amplitude of these backgrounds, if we redshift today, actually can be very large, of the order of omega gravitational waves today of 10 to minus 11. Remember that this is the fraction of the logarithmic spectrum of energy density of gravitational waves to the total critical energy density today. And this is considered to be large. But unfortunately, as it happened with the sector when there were only scalar fields, essentially, these backgrounds are always peaked at very high frequencies if I want to have a really significant amplitude. So very unfortunately, even it's so interesting, you know, these scenarios, because you could really have these multi-peak signatures that would allow you, if you were capable of detecting them, to do a spectroscopy of particle couplings. Fortunately, there is no high frequency detectors that could that are envisaged to work with this amplitude. So I'm afraid this is a bit out of the scope. Okay. Too bad. This is a pity, but c'est la vie, as they say in the French language. So, well, what we've seen so far is that the scalar preheating can give rise to very large production of gravitational waves. If we add gauge fields to make it more realistic, we also see that there are not only large gravitational wave production, but also multi-field peaks, unfortunately also at high frequency. What happens if we add fermions, which would be also a requirement to do more realistic theory? Well, you also produce gravitational waves in large amplitude, maybe not as large as the bosons, but since I have to choose topics, you know, I've decided not to cover this, and just to leave you with a couple of references if you are interested. Here we've worked out what is the production of gravitational waves from the non-perturbative particle excitation of fermionic species. If you want to know more about this topic of reheating, I think some people were asking me in private, in particular, how to embed the standard model of particle physics or other properties of the stochastic gravitational wave background we've been describing. Well, I leave you with these references for the standard model embedding. This is a particular paper for Higgs inflation. And I leave you with these two references, for instance, for looking for spatial anisotropies in this gravitational wave background. Okay? But I won't discuss this because otherwise it would take me too long, the tour, to go into the details of that. Okay, again, let's put ourselves in the perspective, in the global perspective of everything we've seen so far. We've seen that there are several mechanisms of reheating the universe through non-perturbative effects, which could be parametric resonance or tachyonic instabilities, or maybe others that I haven't discussed. These give rise to a large production of gravitational waves, but typically at high frequencies. Okay. Now we are gonna think, however, only in phase transitions, and we've already covered that there is a large production of gravitational waves in the case of hybrid preheating, but as we said, only at high frequencies. Let us imagine, however, that reheating of the universe had finished. So you've produced a distribution of fields which, through their own interactions, they have thermalized. So now we are going to study the more traditional picture of a phase transition within the thermal universe after the completion, after reheating was completed. Okay, so essentially we continue in this third lecture, and we continue actually discussing phase transitions, but now we are going to discuss thermal phase transitions, which means transitions or phase order, first order phase transitions, which are triggered in the context of a universe which is already filled up by a thermal ensemble of relativistic particles. Okay. Very good. So imagine we have already that situation. The universe is the energy budget of the universe. It's filled up by an ensemble of relativistic species. This is the standard picture of the hot Big Bang universe. And the universe is expanding. And as the universe expands, the temperature decreases. So we have to apply now thermal field theory techniques to study the effective potential of, say, a Higgs-like field. Now we have that. Could be the Higgs of the standard model. Could be the Higgs of another scenario beyond the standard model. Okay? A Higgs-like field. So essentially, it is possible that due to its interaction with the plasma, at certain temperature above a given critical value, there is again a single minimum. However, as the temperature of the universe drops, simply because we are in expanding universe in a thermal background, then you see the effective shape of the potential of the Higgs goes making some plateau here, then developing a new minimum and eventually a deeper minimum. Okay, this is maybe the most common picture you are familiar with for understanding phase transitions. But in reality, it's very similar to what I was discussing before. The difference is now we are in a thermal universe, and then there are two mechanisms by which you can actually, let's say, get your Higgs jump from the initially symmetric vacuum into the new broken vacuum, into the true vacuum expectation value. You can actually be activated by thermal effects through thermal fluctuations, or you could also have a probability of tunneling, okay, and then you could have a situation in which the Higgs simply quantum mechanically jumps directly into some region here, and then it will roll towards the true BEV. Either way, what happens, the result of this, is that you produce bubbles, very similar as I showed you before in my three-dimensional simulation. And these bubbles are manifested in a space as spherical configurations, as you saw in the picture I was showing before. Again, due to the difference of pressure between the plasma outside and the true BEV of the Higgs inside, essentially, in order to minimize energy, they tend to expand themselves, and eventually they collide. The difference now, compared to the collisions before, is that now they collide while they are coupled to a thermal ensemble of particles, which is in the media surrounding them. So now we are going to have a bunch of sources, actually, of gravitational wave production, no? Because you can imagine that this collision of the bubbles is very violent from the energetic point of view, just as the one I showed you before, except that now there is this thermal ensemble surrounding the bubbles. So on first place, there is the collision of the bubble walls. This is going to be a highly anisotropic event. Therefore, there's going to be a large anisotropic stress producing a lot of gravitational waves just from that. On top of that, because as I said a couple of times, the Higgs field of these scenarios is coupled to the thermal ensemble in the media, this is going to stir up the plasma and is going to produce waves of pressure, which are called sound waves, okay? The same as we do in air, but here in a primordial plasma of particle species. And depending on the circumstances, you may even produce a turbulent motion in this plasma, okay? Furthermore, if there are gauge fields already, populating the universe, possibly in the form of long coherent magnetic fields, certainly of size larger than the bubbles, then you could even have very interesting so-called magneto-hydrodynamical turbulent motions. Okay, I'm not going to cover this in detail, but well, it's interesting to have in mind that this is a possibility. So essentially, we can model all of these sources. It's very simple. We already have most of the techniques to do it. For the collision of the bubbles, we just need to follow the Higgs profile. In particular, you just plug in the gradients, the spatial gradients, you take the transverse faceless part, and that's the source of gravitational waves. For the presence of gauge fields, as I discussed in the case before of the phase transition in hybrid preheating, you just plug in the electric and magnetic field configurations. And for the motions of the plasma, we have to switch into hydrodynamical view, in which you describe the pressure, energy density, and velocity of the plasma itself. Well, you can do it. Now the codes, the numerical codes, become more elaborated, because you have to mix the distribution of the Higgs field and possibly gauge fields with the distribution of your plasma, but you can do it. And altogether, you plug them in your equation of motion of gravitational waves, and you work out what is the spectrum of gravitational waves coming. Now, before I show you the result of that, let us emphasize something which should be to some extent obvious. So the production of gravitational waves here from a first order phase transition is a causal mechanism, okay? And a causal mechanism, like the preheating scenarios we were studying, means that necessarily the frequency, it has to be some value larger than the Hubble scale. And the way to parameterize this, for historical reasons, instead of putting a parameter here, they put the inverse of a parameter. So this parameter has to be smaller than 1. Let's call it the epsilon parameter. So for any case I have, say I have a particular microphysics scenario, which gives me a phase transition, you should be able to compute the epsilon parameter of this phase transition. Now, before we enter into determining what characterizes typically this epsilon parameter, let us emphasize the following. And I hope this answers also a question I got the other day by someone about what controls the frequency of these backgrounds today. Essentially, what controls the frequency of the background is the energy scale, so the Hubble rate, times modulo this parameter, which depends on the details of the microphysics. So take this frequency at the time of emission, redshift it, just multiply by the ratio of scale factors till today, and you have the frequency today. And then there is a master formula that you obtain from this operation, at least for a thermal universe, which essentially tells you the frequency today is of the order of 10 to minus 5 hertz times this parametrization of the scale of the temperature. So it's linear in the temperature, normalized to something of the order of electroweak scale, modulo this parameter, which depends on the microphysics. Now, why is this parametrization relevant at all? Well, because typically for a standard first order phase transition, this epsilon parameter, it's typically in the range of 10 to minus 2, 10 to minus 3, 10 to minus 1, something of this kind. And you realize that if you plug in actually the electroweak scale here, this means that this hits necessarily the millihertz or around the millihertz range, which happens to be the frequency of observation of the will-be first experiment measuring gravitational waves in space, LISA. Okay, so I think because of this, there's been a new renewed interest in this idea of the electroweak phase transitions, because essentially you can think of BSM, so beyond the standard model physics, that makes first order the electroweak phase transition, and hence you will have a possibility of observing this signal at LISA. Okay? Now, what controls this epsilon parameter? If you want, what controls the location of the peak of your gravitational wave background depends on the bubble properties, which depends on the microphysics. For instance, suppose there is a duration, a given duration for your phase transition. This is parameterized by this inverse beta. Therefore, depending on the velocity at which the walls propagate in the plasma, which that depends on the interaction with the plasma, there will be a typical size of the bubbles upon collision, just when they reach each other. So essentially, roughly speaking, for the production of gravitational waves from the collision of the bubbles, epsilon is roughly speaking given just by the ratio of the duration of the phase transition compared to the Hubble scale time, okay, which normally is expressed inversely like this. Or if you want, for the production of the gravitational waves from the sound waves in the plasma or the turbulent motions, typically what matters the most is rather the radius, among other aspects, upon the collision of the bubbles, okay, after the collision of the bubbles. So altogether, there is, if you want, for any microphysical model, there is a number of parameters characterizing your phase transition. There is the duration, there is the velocity of the plasma, which can be, of the wall propagating against the plasma. This can be very complicated function. There is the energy scale at which all of this happens. There is the amplitude today, which can be of the gravitational wave background itself, which can be parameterized in a very simple manner. It depends on the epsilon parameter again. And it depends also in these alpha and kappa parameters, which simply characterize the ratio of the energy density of your source, of the Higgs-like sector, compared to the total energy density of the background. Okay, and essentially it can be written like this: kappa times alpha divided by 1 plus alpha, where alpha is the ratio of the vacuum energy density inside the Higgs bubbles to the ratio of the thermal plasma, and kappa is the ratio of the kinetic motion, of the kinetic energy of the motion of the walls compared to the vacuum energy inside the bubbles. This is a very simplistic picture. It's not the most general parameterization. You can elaborate it a bit more. People have worked it out this in the last years. And in particular, people have added hydrodynamical effects and turbulent motions, as I was saying. So the whole thing gets very complicated. And instead of showing you complicated formulas, I'm going to rather show you some discussion on the results. Okay. So to really participate as a researcher nowadays in this business of evaluating the signal of gravitational waves from first order phase transitions, you need, first of all, to understand what is the analytical aspects of the bubble collisions, which can be done to some extent analytically. But then nowadays, many people are switching into numerical simulations of these bubbles. Okay. Then there is the creation of the pressure waves, the sound waves, which can only be done with numerical simulations in hydrodynamical codes with scalar field dynamics. And here I think the people leading the game, or certainly who started, is the group of Heimers et al., okay, together with David Weir. And there's been both numerics, both analytics attacks, but I think at the end of the day, you have to resort mostly to numerics. And then finally, if you want to take into account turbulent motions, well, there's been analytical evaluations, but I think these are particularly rough or complicated. And very, very recently, people have started finally to sample or to probe these aspects through numerical simulation. So essentially, altogether, they have made very lively this field. And this field is very interesting because this field of phase transition is very interesting by itself, not only because you produce gravitational waves that could be potentially observed, it's just because phase transition themselves actually represent a connection between particle physics and cosmology, since it is actually the microphysical models of particle physics that can lead really to these scenarios, no? And you really have to understand what are your the specific parameters and details couplings in your scenarios of particle physics. And furthermore, by opening up the possibility of detecting these backgrounds, we are essentially providing a new proof of BSM complementary to colliders. As we said, naturally, LISA, the experiment that will be looking for gravitational waves in space, can look for the electroweak phase transition, or if you want phase transitions, maybe in a hidden sector, but around these energy scales, electroweak scale. And if, on the contrary, you look just for high energy scale phase transitions, then you go into high frequency range of phase transitions, for which is very difficult, unfortunately, to have a detector. So how does it look, the typical signal of a phase transition? Well, it's a signal that typically can have one peak or two peaks, which depends on the scenario you are considering. Here I'm showing the spectrum of gravitational waves today versus frequency. And here I'm showing different sensitivity curves of the LISA experiment when this was under discussion. Nowadays, you should only look at the red curve here and forget about the others. At the red shade here, this is the sensitivity curve for LISA, more or less, that has been adopted for the LISA mission. And what you see here is one example in which there is two contributions, one from the collision of walls in blue, another one from sound waves in green. And then the total spectrum is the superposition with this double peak of the two effects. And here we see that there is also contribution from MHD turbulence, but it's completely subdominant, so there is no much of contribution to the total signal. Now, if I were to ask you what is the most relevant aspect of this plot, maybe you would tell me, it has two peaks, this is very characteristic. But I think what is really amazing is the fact that we are discussing about detecting these backgrounds directly with interferometers, as much as LIGO has done, LIGO and Virgo, with the detection of transient signals from binaries of massive objects. Okay. Now we are discussing about measuring a signal that comes from a very tiny fraction of the very early universe, which will carry information about particle physics. So LISA essentially is the experiment to go for, and it's going to be probing a range of scales spanning close to 5 orders of magnitude, okay, these scales here. And as I said, repeated number of times, it can probe electroweak phase transition, embedding, for instance, the standard model into some extensions. Simple extensions would be having a singlet, or direct coupling of Higgs to scalars of whatever extension, or having higher dimensional operators, etc. And now, if you forget about the electroweak phase transition, you could think of dark sectors, which do not talk to a standard model directly through interactions, only gravity. And there are some candidates that provide, for instance, a dark matter candidate and confining phase transition of pure gauge fields that corresponds to first order phase transition, and you can tune it to give a signal within LISA. Or you could go even talking about extra dimensions. Okay? So the question is, can we really detect a first order phase transition? If we do so, what will we learn? Well, it's clear that LISA, the experiment, will have the capability in the 2030s, but it's also clear to people working in FINO for high energy physics at the LHC, that the LHC is actually putting pressure all the time into many of the BSM extensions that would promote the otherwise crossover electroweak phase transition in the standard model into a first order one. Now, assuming LHC does not rule out all of the models we need, which I think is pretty clear, it will not. There's always a scenarios that you won't be able to rule out completely with the LHC. Well, it's clear that LISA can constrain and even possibly detect some of these backgrounds. Now, the problem is these predictions are very complicated, the many assumptions. In the case of some waves, mostly they are relying on numerical simulations. So there is the question to what extent our modeling is entirely correct. And this is a difficult discussion, but it's certainly one we need to have in the community. And the second one is that even if we detect a signal, then all we can infer from that signal is the typical alpha parameter and beta parameter. I recall you alpha was the ratio of energies between vacuum energy and thermal environment energy, and beta was the inverse of the duration of the phase transition. So essentially, you are not going to be able to tell the exact details of the BSM model behind this phase transition. You are going to have a bunch of family models compatible, okay? But well, again, c'est la vie. At least we would be really detecting something completely beyond the standard model. Okay, so far so good. I hope for phase transitions that produce a large gravitational wave signal. As I said, this can be happening in scenarios before we have produced a thermal universe, which is at the end of inflation in hybrid preheating, or it can be produced in a thermal universe through the triggering of first order phase transitions if the appropriate conditions are met, such that we have some situation in which maybe a Higgs-like field tunnels or simply jumps through thermal excitation over a true BEV that its effective potential has developed. Okay. Now we're going to change gears and we are going to start discussing cosmic defects, which are a possible outcome after a phase transition. But I think before we really move into cosmic defects, that we will see they have two possible contributions of gravitational waves, one an irreducible signal, and another one a large signal due to, in the case of cosmic string loops in particular. Before that, I think I'm going to propose the organizers to take a coffee break, if it's fine, and then maybe I can either address some questions and maybe. So we are a bit ahead of time for once, which is good. Maybe we could resume at 35, and I'm happy to take some. Yeah, I'm happy to take 5 minutes questions and then another 5 minutes break to take some merienda, etc.
Sounds good. I'm back, Enrico.
Okay, so, great, John.
So did you take the question from Tessio or?
No, not yet.
Okay. So Tessio is asking, defined temperature effects in phase transitions are usually taken into account with a thermal effective potential. But apparently, there are some issues with the use of the effective potential because it gives case-dependent results. Can you comment on that?
Case-dependent results. Well, I know the issues are that, of course, these thermal field theory corrected potentials are based on perturbation theory. And there can be a breakdown of perturbation theory when you approach to the actual phase transition. So this is an issue that I actually don't know to what extent people working on these particular theoretical aspects have really resolved in detail. Other than this, I'm not sure what other aspect or failure you might be referring to. What I know is that it is possible certainly to simulate numerically some of these potentials and I'm actually working on these ideas, trying to capture from a purely numerical aspect the whole presence of, say, the plasma and gauge fields and all of this. And then hopefully you can capture all the effects without having to rely in any explicit analytical form, which is based on some regime of perturbativity. But it's a good question that, to what extent is it solid and robust, the actual underlying technique we are using? I think I'm pretty sure it's debatable, depending on the scenario and the circumstances.
Okay, cool. I think next Roger is asking a question.
Mm-hmm.
Okay, I will read it. So any consequences to the scalar perturbation power spectrum from these thermal phase transitions that can be observed?
Well, I think certainly any of these large inhomogeneities, like the ones in preheating that you remember you are producing exponentially large occupation numbers. This translates into an inhomogeneous distribution of the field configuration. And here is the same with bubbles, no? All of this is gonna create a large distortion in the otherwise homogeneous background metric. So in other words, it's creating large gravitational waves and it's also creating large scalar perturbations, as this person is asking. But one should realize that these are very small scales compared to cosmological scales, because all these causal phenomena are taking place after inflation. Therefore, the characteristic scales of them, it's sub-Hubble in that moment. And that's already a very short scale, compared, for instance, to the scales at the CMB, which are those scales that left the Hubble radius during inflation some 50, 60 EFOs before the end of inflation. So they are exponentially separated away from the scales we are dealing with now. And this is the problem, that these scales are so short that at the end, through interaction and thermalization effects, we are going to erase them. And I doubt there is much of an observable remanent effect at the end associated to scalar fluctuations here. One possibility could be if you produce very large scalar fluctuations during, I'm not sure about phase transitions, but certainly during preheating, some people have speculated with this, you could produce primordial black holes, because you produce so large scalar fluctuations in the metric that essentially they can collapse into a black hole because they contain so much energy. This is a possibility, but again, it doesn't have much of observational consequences because they are also tiny, very tiny black holes compared to the ones you could produce from large scale fluctuations excited during inflation. I really hope on the lectures on dark matter they cover a little bit that, but I'm not sure. So here you would produce very small scale black holes that they would evaporate rather soon, okay, because they are tiny to some extent compared to the other ones you could produce from large scale fluctuation from inflation. So again, I'm not aware, I believe there is not effects observable from here. But, okay, I'm not 100% sure about all the literature in this particular aspect.
Cool. Next, Lucas is asking, could we also expect the same sort of effect from other phase transitions, like for instance in QCD phase transitions?
It's more difficult, like QCD phase transition in the standard model, so in QCD of the standard model, is a crossover, okay? Which means it's a smooth transition between phases, okay? Whereas here, what we need is the nucleation of bubbles. So in order to make a first order the QCD, you would need very large chemical potentials for neutrinos. And I'm not sure if this is realistic or needed or to what extent a possibility. If you think, however, of a hidden phase transition similar to QCD in the standard model, but simply of a beyond the standard model sector, which is decoupled from the standard model, then it's possible to have a first order phase transition in these other scenarios involving gauge fields, non-linear, non-abelian gauge fields. And yes, that's a possibility. But I think it's more natural to think about it out of the standard model. I would propose now, Joan, because it's 30, now we take a real break, 5 minutes, and in 5 minutes we reconvene. Okay. And if you want, we answer a couple more of questions before I continue, but let's take real.
Sounds good. Let's take 5 minutes break.
Excellent.
See you in a bit. Ciao.
Okay, I'm back whenever you guys want.
Okay, so I'll pass you the last question that was
Okay, excellent.
left unanswered by Lucy, that she's asking. If we know that the curvature of the universe is 0, what shape does the universe contain? In what structure is the universe contained? It doesn't seem of gravitational waves, but maybe you can answer.
Okay, so, well, first of all, be careful with saying we know the curvature of the universe is 0, because what we know is from observing the anisotropies of the CMB together with other probes, that the parameter that controls the curvature of the universe is small enough so that we can claim that our observable universe, or within our Hubble radius, is essentially flat, okay, Euclidean type. But we do not know the global structure of the universe. We don't know what are the boundaries of the universe, if there are any. We don't know if the universe is infinite or if it has a finite volume. So essentially, we don't know whether, if you go to scales much larger than what we can access through beyond our causal domain, whether there could be some spatial curvature in the universe. We don't know. And actually, there are some inflationary models that do predict this in the very large supercosmological scales. Okay, so the only thing we know is that in our observable patch, which we don't know what fraction of the total universe that represents, we are essentially mostly Euclidean spatial space, and yet there are tiny curvature fluctuations, which are precisely the one that cause the CMB anisotropies. Okay, so there is always a minimum amount of fluctuation of the curvature, which is precisely what causes the anisotropies in the CMB. I'm not sure to what extent this is related to gravitational waves question, or maybe I was misunderstanding the question.
Okay. I think it was answered, but if it wasn't, please let us know, Lucian. Okay, it seems it was answered. She says thanks. So there are no more questions. If you want to continue.
I'm happy to continue, yeah. Okay, very good. Okay, excellent. So we were here. We were about to start discussing cosmic defects. I will explain now what cosmic defects are. Just want to highlight before that we are going to see two contributions of gravitational waves produced by cosmic defects. So cosmic defects are the aftermath product of a phase transition, a possible aftermath product, okay? Because not in every phase transition you produce cosmic defects. Essentially, the pioneer of the field is Tom Keeble, whom you know is also the pioneer, together with others, with Higgs himself, of proposing the Higgs mechanism, which later on was generalized to the standard model by Salam and Weinberg. And essentially, Keeble was someone very clever who not only understood the Higgs mechanism, but also understood that some of the consequences of the Higgs mechanism in the global context of the universe. Essentially, he understood that whenever you spontaneously break a symmetry, like in the Higgs mechanism idea, to provide masses to the particles coupled to the Higgs-like field, certain type of structures that he called domain structures here, nowadays we call them topological defects, can arise in the universe. Okay, why is that? Because if you think of a situation characteristic of a phase transition, or in general a spontaneous breaking of a symmetry, essentially you have a Higgs-like field, which initially, we saw examples of this before, maybe due to thermal contributions, or maybe due to its interaction with another field. Essentially, it has a single minimum, a given group of symmetry, then you break this symmetry, and you end with a situation where you have a new set of degenerate minima, which we call the vacuum manifold, and you have reduced what is the symmetry of this vacuum, okay? Or if you want the new vacuum, do not respect the original symmetry. It may contain yet a subset of the freedom that was in the original symmetry, okay? But it's certainly a smaller group of a symmetry. So now what's important is, in this vacuum manifold, you should think of it like a location of points in this internal space that we call the vacuum manifold, where the Higgs field of the problem is pointing to a given direction in different places in space within all the freedom it has in this vacuum manifold. Here, for simplicity, I took the breaking of a U1, okay, a billion gauge symmetry. So therefore, there is a circle where the Higgs field is a complex vector, can take values. Essentially, the picture, what Keeble realized is that in different locations of the universe, due to causality, the Higgs is going to point inside its internal vacuum manifold in a given direction, which is going to talk to each other. So it's going to align the direction of the Higgs within that internal manifold. But in some separated region, if you want separated enough from the previous one that there is no causal contact, the direction is going to be completely different, arbitrary, if you want. Okay. So let's see how this happens in detail. Imagine you do have a spontaneous symmetry breaking situation with, for simplicity, with a Higgs-like field with its typical Mexican hat potential, and then there are interactions of this Higgs field with either external degrees of freedom. In hybrid preheating, this was an inflaton, or with a thermal bath. We already saw that this is one way to trigger a phase transition depending on thermal effects or field interactions. Now, let's suppose we take a two-dimensional slice of a three-dimensional space, okay? We cut the universe and we represent now y and x axis in this two-dimensional sheet of a space. Now, the Higgs within its internal manifold in these situations of a phase transition, it's gonna point into a different direction in each location in a space, okay? Now, we put together in this particular point, origin of this coordinate system, and we see that the arrows within its internal manifold of the Higgs is pointing to completely opposite directions. So essentially, somehow the field, the Higgs field here, has to take some continuous smooth deformation such that its direction in the vacuum manifold goes changing as you go around this point, okay? But do realize that in order to have a length for this vector, it means that the Higgs is in the true BEV, in the broken vacuum. But what's going to happen here in the center of this spatial location? If the Higgs is pointing in different directions in every of these corners, when you approach here close to the center, the problem is that the Higgs is going to be forced to go to zero. Because while you have a length in the vacuum manifold, you are in the broken BEV, so you do have a length. But when you come here, you cannot be pointing at all the directions. Or the only way to do it, if you want, is that the Higgs climbs up on top of its potential, of the Mexican hat potential, to the top, and then it goes to phi equals 0. Okay. Well, this is the underlying mechanism to understand the origin of the formation of topological defects, which if you've never seen before, is probably difficult for you to grasp what I'm really saying. But when there is a situation like that, essentially depending on the microphysics, so what is the symmetry you break, you can produce cosmic strings. We actually saw a picture of that, and now I'm going to show it more. You could produce monopoles. Gauge monopoles are forbidden due to cosmological overclosure of the universe, but global monopoles, for instance, are okay. Or you could have so-called non-topological textures, which are also cosmic defects, which essentially consist of spatial configurations of the Higgs pointing into different directions in the vacuum manifold, but always interpolating smoothly from one to another. Okay? It is the microphysics that determines what is the cosmic defect you really form. And if you remember, we were seeing already in this simulation snapshots I was showing of the phase transition at the end of hybrid inflation through the hybrid preheating mechanism, that there was the nucleation of the bubbles of the Higgs, that the Higgs amplitude grew inside the bubbles, and the bubbles grow themselves in size, eventually colliding. And we pointed out that in between these bubbles, there were some yellow traces. Unfortunately, it's not very visible in this picture, which meant that the Higgs had a much smaller value than the value actually it has inside the bubbles. And this is precisely what I've been describing before. Okay, these are precisely the cosmological defects. So for instance, here in the color coding, I'm showing the face of the Higgs pointing its internal manifold, which is a circle. And you see it's changing or circulating, wandering around in this particular vertex from 0 to 2 pi. So clearly the Higgs, if you imagine a vector represented by the colors, is wandering around. But when it comes to this location, the Higgs is forced to climb up its potential, and therefore it has a 0 value, or at least a much smaller value than the true BEV. And this is precisely what I'm plotting here. I'm plotting the position, the location of points in three-dimensional space where the Higgs has a minimum. And what you see is that the shape of this is elongated structures that we call cosmic strings. If we look, as I show already this picture, into the energy density of gauge fields that are coupled to the Higgs, actually this is even more clear, because now we see that the concentration of energy, in this case, I think I'm representing the magnetic field energy density, it's clearly placed in elongated structures, okay, in the cosmic strings. So I have on the one hand the zeros of the Higgs in these locations, and on the other hand, I have the maximum values of the energy density of gauge fields, which they tend to go where the Higgs is 0. Very good. So the type of defects you produce really depends on the physics you have, on the microphysics of your scenario, on the symmetry breaking pattern. You could have something called domain walls, which actually are kind of forbidden unless they decay, but okay, you could technically produce them. You could have cosmic strings, as I'm showing. You could have cosmic monopoles, only global ones are allowed, or you could have non-topological structures. Either way, it is the causality and it is the microphysics that determines what type of defect you have, and it is causality actually that tells you the following, and this is very important observation that Keeble made. There is always a correlation length, so a typical length scale, which, if you want, is a fraction or some parameter times the Hubble scale at every moment. And essentially, this correlation length tells you about the typical distribution of the defects in the universe. Okay, so for instance, if these are monopoles, immediately this correlation length is the typical distance between monopoles. If they were cosmic strings, you should think of a string coming here transverse to from the screen, from the file itself. Okay, and then this is the typical distance between the core of the strings. And if these are, for instance, non-topological textures, you should really think of this as the scale of changing orientation of the Higgs vacuum manifold within its internal space. Either way, the great insight of Keeble, already more than 40 years ago, he realized of the following. So not only there is this correlation length, the distribution of defects is actually going to enter into a regime that we call scaling, or that he called scaling, which means that the fraction of this correlation length to the Hubble radius, to the causal distance in the universe, is actually constant. And not only is constant, but it's also further one, which means that the correlation length is always following, tracking a scale of the same order of the Hubble scale or of the causal scale in the universe once the topological defects or the cosmic defects have been formed. Okay, so in other words, if you want, I can follow momenta of the distribution of these defects by measuring momenta around the, here is comoving momenta around the comoving Hubble scale. Okay, or if you want momenta, comoving momentum multiplied by conformal time. Okay, which is the inverse of this comoving Hubble scale. So pictorially, what scaling really means is that imagine you have a phase transition in the very early universe, you produce a bunch of defects all over in the universe, and very soon their correlation length tracks down the Hubble scale. As the universe expands, the Hubble radius also grows, proportional to time, and essentially the typical distance or distribution of the defects becomes self-similar to itself all the time, just scaling the typical distance to the Hubble scale. Okay, so essentially it always maintains the same distribution. It goes moving. Okay, so I'm talking about the statistics. So statistically, it resembles to itself all the time, just scaling the amplitude of the typical distance to the current Hubble horizon in every moment. Okay, that's what scaling means. Okay, excellent. Now, yes.
Excuse me, Daniel, maybe I can pass you a couple of questions.
Okay.
From what you're discussing.
Yeah.
So there's a question from Ganesh. He's asking,
what is the size of the box? Is the size of the box important for the simulation?
When we simulate cosmic defects, the size of the box can be very important if we want to follow the cosmological history of the evolution in scaling of the cosmic strings. Yes, and it gives us a lot of limitation. The typical volume boxes we are using are 1,000 cube points per dimension. Nowadays we can manage to do 2,000 cube, 4,000 cube. We are even managing to do 8,000 cube. But never more than that. So we are always limited in the range of time scales and separation of scales we can prove in our simulation to this limitation, yes.
Cool. Then there's a question from Korbar. It's from some slides before. The question is, what do you mean by global monopole, if not Tov-Polyakov monopole?
So by global monopole, I mean simply that if you break spontaneously a O3, global theory. So imagine you have a Higgs-like field with 3 components. There is no gauge interactions, and you break O3 into O2. Okay, then you produce this global monopole, which is just a spatial spherical configuration of your Higgs-like field, which has a spherical symmetry and is global in the sense that it's made only of a scalar field only. That's what is called a global monopole.
Cool. Last question. So Tesio is asking, what about the correlation lengths for domain walls instead of cosmic strings?
So the correlation length for any type of defects would track the Hubble radius. The problem with domain walls is that if you don't make them disappear, decay into something else, then they tend to overclose the universe. So for instance, if you have a theory which is only global and breaks a set to symmetry, that's a Higgs field that has only one direction. It's a single component Higgs field. And breaking the set to symmetry, it means that either now takes a negative BEV or a positive BEV. Okay, that gives rise to cosmic domain walls. And unless you couple them to something else to allow them to decay, this poses a serious problem because they will overclose the universe. There are, however, other scenarios. For instance, when you have an axion-like field that produces, by whatever the mechanism, a structure of cosmic global strings and domain walls. These domain walls eventually decay, and then therefore there is not much of a problem with them. Okay. So this really depends on the scenario. Shall I continue?
Yes, please.
Okay, now, because we know any type of defects are in scaling, now let's ask ourselves, what is the gravitational wave production from a scaling network? After all, the scaling network means relativistic motion of these objects, which they are going at the speed of light because they are tracking the Hubble scale, okay, which is growing at relativistic speed. So essentially, now we have to compute the energy momentum tensor of whatever these cosmic defects are made of, scalar fields, or let it be also gauge fields, and then take the transverse choiceless part. Now, there is a general formalism that I had not introduced so far, which tells me that the spectrum of energy density, logarithmic spectrum of energy density gravitational waves, saying co-moving scales and conformal time, it's actually given, there is this master formula, by this double time integration over expansion history of the universe times a green function times this object, which is called the unequal time correlator. What is that? Is the 2-point function of 2 copies of the transverse choiceless part of the energy momentum tensor of whatever source of gravitational waves. Now, what happens is that the computation of this 2-point function, which can be very complicated, okay, we represent it here by pi squared, an equal time correlator, unequal because it's 2 times at which I'm computing the correlator. It's very complicated. But because we are in scaling, actually we can use our understanding of scaling, and we know that whatever this correlator looks like cannot depend explicitly on the scale, because we know the scales always track the Hubble scale. So in other words, it can only depend in these dimensionless variables, k times conformal time, which remember is nothing but k over co-moving Hubble scale. So now we plug in this knowledge here, that the functional form of scaling of an equal time correlator in scaling has this particular shape. And we consider the case for the time being of radiation-dominated universe, which means the scale factor in conformal time is linear. Okay, And now if you look at this master formula that tells me the spectrum, essentially I have a power of k to the 3 here, but now if you count the powers of time you are left with, essentially you define these dimensionless variables I was talking about, and you introduce your scale dependence from outside inside, and what happens is that suddenly all of, like almost magically, you are left with a dimensionless integral, where you don't see the scales anymore, because since the scales always track the horizon, essentially you don't see explicitly any scale. So essentially what I have just demonstrated, maybe a bit fast, so please have a look yourselves afterwards in the transparencies, following the steps, that the production of gravitational waves, just from the fact that we are in scaling, it's always a scale invariant background of gravitational waves. The scale invariant because the amplitude does not depend on the scale. And the amplitude of this scale invariant background is essentially characterized by the vacuum expectation value of the phase transition that gave rise to the defects in first place, so by the energy scale of the moment of the phase transition, and by this dimensionless integral that I was writing before, which is characterized by the unequal time correlator in scaling, which unfortunately we can only get in a reliable manner from lattice simulations because that's a very nonlinear object. Now, realize that what I'm saying here applies to phase transitions of any order, first order, second order, crossover, whatever you want, and for any kind of defects as long as they are in scaling, okay? And this is why we call this the irreducible background of gravitational waves from any scaling network, because this applies to any network of defects. If we generalize to matter domination also, or together with dark energy if you want, at the end of the day, the final spectrum of gravitational waves today essentially is made of two pieces. On the one hand, there is the constant part of the modes radiated during radiation domination, and on the other hand, there is the second part, which has some now scale dependent, which comes on the modes that were emitted during matter domination. Essentially, there is a constant here, very similar to the previous one, dimensionless constant, which boils down to characterize the strength of this part. Okay. Now, if I plot you how these spectra look like, it's always as follows. There is a plateau corresponding to the scale invariant part from modes emitted during radiation domination, and there is this bump coming from the emission during matter domination. Now, this bump is always localized at the frequency corresponding to the transition between radiation to matter, which is a very small frequency. So essentially, from the point of view of observation, say from direct detection experiments, or for other techniques like pulsar time arrays, that is somewhere here in 10⁻⁹, 10⁻⁸ Hertz, we only care about the amplitude of the plateau, of the part emitted during radiation domination. You see, depending on the scale, on the energy at the phase transition, so the BEV, the vacuum expectation value of the Higgs field, essentially this controls the overall amplitude of the spectrum. And depending on the multi-component field Higgs scenario you have, so what type of defects, for instance, this is the case of global strings or global monopoles or textures of any kind, you also modulate, you also obtain what is the scaling of the final amplitude depending on this guy. Okay? So this signal is very interesting because if you want, it mimics the one from inflation, which was, if you remember, a quasi-scale invariant background of gravitational waves, but it has a way larger amplitude than the one from inflation for the upper bound that we can take of the energy scales for cosmic defects. Now, there is, however, another contribution to the production of gravitational waves from cosmic defect networks. But this contribution only comes into the game if... Yes?
Can I ask you a question before you...
Yes, sure, sorry. Yeah.
Can you give just a bit what is the essence behind the computation or the simulation of the unequal time correlator? What are you actually simulating? And
yeah, sorry, I'm going in the wrong direction. Yeah, sure. So what we are simulating really is a grid, expanding grid. Okay, when we simulate these things, we are having a box, a lattice, which represents co-moving coordinates. And then we actually represent our field theory living in this box, and we trigger a phase transition. with the typical conditions in the microphysical modeling of our phase transition that leads to the production of cosmic strings, okay? And you saw an example of this already, no? Here, this is just a phase transition where I'm seeing how the cosmic strings are being formed in my lattice. Now, after we do this, we do some trick of diffusion, which is like some, how to say, faking in somehow the dynamics such that we enforce the system to get closer and closer to scaling as much as as fast as we can. And then at some moment we stop this diffusion, and then we let the whole network of cosmic strings to evolve, and eventually it reaches scaling. Okay, and there are several observables by which we can determine the network is in scaling. So then, literally, in our three-dimensional distribution of our lattice, we take a measurement of the energy momentum tensor, in particular is transverse traceless part, okay, which is a three-dimensional guy. We convolve it, we multiply it, sorry, by another picture of the three-dimensional energy momentum tensor distribution at a different time, and we go taking these products at different times all the time. Okay, so if you want, we fix the initial time, and then as the simulation goes on, we take another picture, we multiply, then eventually we take another picture, we multiply, and so on and so forth. And now we repeat this operation a number of simulations, and this is what these brackets represent. This is a statistical ensemble average over the realizations of the energy momenta tensors of my distribution of the network of cosmic strings, of which I read out exactly three-dimensionally the transverse traceless part of the energy momenta tensor. That's how we do it. Another way we can do it nowadays in a paper that actually I think for the first time will demonstrate the equivalence of this technique with the idea of solving directly in real space, locally in space, the actual production of gravitational waves, is that we are now solving, and hopefully this paper will appear maybe even next Monday or next Tuesday. We are solving in the lattice directly the wave equation of the gravitational wave tensors during expanding history for which we simulate the defects, and we plug in here directly the source, either scalars or gauge fields, okay, as the source. And then, so we can do both techniques, you know, we can actually do both techniques. But you have to go numerical all the time if you want to have you know, how to say, trust in what you are predicting. And even that is very difficult because there are many limitations, as somebody asked me before about the limitation of the box volume of the box.
Okay, thanks.
Okay. So now, as I was saying, I had been discussing so far the irreducible production, but if the defects we form are cosmic strings, actually, there is an extra emission. And funny enough, historically, what people really realize in first place is this extra emission of gravitational waves. Okay? So essentially, why does happen that we have extra emission is because cosmic strings are very, very interesting objects, and this happens only to cosmic strings, not to other type of defects. And the reason why they are particularly interesting is because you can think of them like one-dimensional objects. They have a width, but if we look far away enough, they look like one-dimensional objects. And essentially, when they self-cross like this, or when they cross two different strings, they can chop off a loop from their whole network. And what happens, this loop, you know, now is disconnected from the whole network of cosmic strings. And it has a lot of energy because these are tubes of energy. So this energy, you know, it wants to be released. So essentially, because now you have a loop at sub-horizon scales, the natural dynamics of the strings makes it vibrate, makes it oscillate. And what happens is that the string starts oscillating and gravitational waves are emitted from the result of these oscillations, okay? It's a way of releasing its tension. It's in a lot of tension, so it naturally vibrates, and actually you emit gravitational waves in a series of harmonics, corresponding to multiples of the inverse of the length of your cosmic string loop. So essentially, depending on the tension, which is essentially proportional to the energy scale that form the strings in first place, you have a series of emission of different harmonics in gravitational waves. The basic formalism tells me that the energy density spectrum can be worked out now as an integral in the expansion history of the universe times this other integral, where I'm integrating, after I take the integration in time, over the length of the different loops, the loop number density, so the amount of loops per volume, okay, and the power emitted by each loop on the average, okay. This can be predicted analytically and can be also checked through some numerical checks, not numerical simulation field theory, but other type of numerical checks. And essentially, it always comes in the shape or in the form of a power law with the frequency and the length of the loop to some power. And depending on the type of loops you have, what are the features, there are kinks, cusps, and even other type of features, you have one power or another, okay? Well, essentially, you put all together, and you typically end with a spectrum of gravitational waves. Here I'm representing omega gravitational waves in log scale versus frequency today, which looks very similar to what I was showing you before, and yet is different. Before I was showing you there is a plateau and there is a bump for the irreducible background. Here now there is a plateau and there is a bump for this, let me call it extra emission from the loops. However, the amplitude of this extra emission can be rather large, much larger than the irreducible background. Furthermore, depending on the size of the loop, okay, you can have a shift of the position of this bump in the spectrum. And essentially, unfortunately, there is a big discrepancy between leading groups in working out the details of the loop number density, which is one of the key ingredients, if you remember, okay, because you have to plug it here. And depending what loop number density you plug in, the shape of the spectra can be similar to what I said, like a plateau and then a bump, or can have this other more fancy shape. Okay, and this really depends which is the group results you use for the loop number density. But the good news is that whatever modeling you use for this loop number density, an experiment like LISA is actually capable of probing the energy scale, which is measured in terms of the tension, mu, which is typically the BeV square. Okay, so you can translate G mu into BeV over Planck mass, all of that square, and essentially can probe 6 orders of magnitude beyond what is being currently done with so-called PTAs, which are here. So essentially, there is a large parameter space of the energy scale of your phase transition that give rise to cosmic string networks that can be probed by LISA. Okay, and this is amazing that essentially within few years, well, maybe not so few because it's still more than a decade, but still, you know, in the somehow near horizon, we'll be able to be probing energy scales of phase transitions down to 10 to minus 17 in the G mu parameter. This corresponds to something like 10 GeV in the BeV, whereas the current constraints from CMB in the possible maximum amplitude of energy scale from phase transition is of the order of 10 to 16 GeV. Okay, so essentially, an experiment like LISA is gonna improve like 10 orders of magnitude the G mu, 6 orders of magnitude the G mu parameter compared to PTA today, and even 3 orders of magnitude compared to the best scenario possible with PTAs, like experiments like SKA, if in case you've heard of this. So LISA, here's a bit of propaganda because I'm part of the LISA consortium. I think is going to be eventually the best experiment to constrain the presence of cosmic strings, possibly the only way to obtain them up to this superb accuracy. And well, imagine if we discover them, this will be a direct detection of physics way beyond the standard model, obviously. Okay, or we will put a stringent constraints. Either way, we win. Now, as a last remark, recall what I said, that the shape of the spectra from loops is very similar of the shape of the spectra from irreducible production from the network of strings, but the amplitude here, if you look at the scale, can be much larger for the loops than from the irreducible background, unfortunately. No, I mean, unfortunately for the irreducible background, sorry, but good for the loops. Maybe one comment I should make is that there is also a huge discussion in the community that all this production from loops relies in what is called the Nambu-Goto approximation to the strings, which essentially is like in string theory. They assume that they are infinitely thin, so there is no width. Okay, and the approximation here is that because you are considering the network of cosmic strings in the whole universe, the real width because they always have a finite width, doesn't really count. The problem is that in field theory simulations, we see that there is this finite width, which is expected, but we also see that these loops rather decay much faster into particles, so the field quanta they are made of, before they can radiate all the gravitational wave that is predicted from the Nambu-Goto picture. So in reality, there's a huge discussion in the community, and the two sides don't agree at all on what is the final outcome of this. Okay? In any case, I think with this, I've covered my third lecture. Just to put you in perspective, everything we've discussed. We've covered the discussion on gravitational wave production from cosmic defects. We discussed first the irreducible background, then now the more specific one from the relativistic motion, if you want, of the oscillations of the string loops, which give rise to a higher gravitational wave background, at least from the perspective of Nambu-Goto approximation. I think with this, we've covered really all the cases we wanted to discuss. Using the thermal universe, we've seen phase transitions of first order, and we've seen cosmic defects afterwards. In the pre-thermal universe, we've seen reheating, including scalar and gauge fields. Before reheating, there was inflation. We've seen scenarios with extra species or symmetries that created a lot of gravitational waves. Or we've seen that inflation in general produces scalar and tensors, but these tensors, unfortunately, are very difficult to observe. So I think we are done. Okay, let me just summarize. These are the 3 lectures, which cover 5 topics. Essentially, very briefly, okay, with no need to extend our summary. For gravitational waves from inflation, from a standard vacuum fluctuation from inflation, there is an intensive search in the CMB. We haven't discussed this in detail because it would have taken us to other techniques and observations, but you do have quite a discussion on this in the transparencies of the second lecture at the very end, okay, in the back slides. And there is, however, the possibility of having extra ingredients, like having an axion coupled to topologically to a gauge sector, which gives rise to very enhanced gravitational wave production. From preheating, typically we always get a very high amplitude for gravitational wave backgrounds, but very unlikely to be detected because this corresponds to high frequency cases. And for phase transitions, for the electroweak phase transition, if embedded in the right BSM scenario, we can have a very large amplitude for this background, and hopefully within the right frequency range of LISA. And for cosmic defects, for instance, in grand unified theories, this is a natural prediction, there is a good chance that experiments like pulsar time arrays or LISA could measure something, or if not, put very stringent constraints. And finally, I leave you maybe with some propaganda, which is the review I have myself with my collaborator, Chiara Caprini, on stochastic backgrounds of cosmological origin, so from the early universe, where you will find in infinitely much more detail everything I've been telling you in these 3 lectures. With this, I'm done. Thank you very much. Happy to take more questions if needed.
That's great. So let's take a couple of questions to be on time, and then let's postpone the rest of the questions for the Q&A or for the Slack.
Sounds good to me.
So Tesio asks, gravitational waves are redshifted in the same way as electromagnetic radiation?
The answer is yes.
Okay, so let's take another question since that was easy. What characterizes, from Lucas, what characterizes the scale of the average lifetime of these topological defects before decaying?
This is a very good question. So in the Nambu-Goto approach, essentially, this depends on the length they have at the time of formation, okay, and the energy store they have, okay. Now, what's happening is that in the lattice simulations, what we see is that these guys decay only depending on the length, and essentially they decay faster than you would have thought, at least within the resolution we can manage to have in the lattice simulations. And therefore, from that point of view, field theory point of view in the lattice, the loops that would be the generators of the whole background of gravitational waves, which is this extra emission, would disappear and wouldn't be there to form this nice background. And this discrepancy and significant difference between field theory and Nambu-Goto has not been really resolved at all. You know, and there is active discussions in the community, sometimes very heated, about this topic. Yeah.
Great. I don't see more questions for now, but if more come, please ask them later.
Yeah, I'll be in the Q&A session tonight, or well, tonight for me, whatever the time for you guys. So yeah.
Okay, perfect. So thanks a lot, Daniel. You covered many things, but it was a lot of fun to follow them. Very clear. So that's it. Thanks.
Okay. Obrigado a todo el mundo. Okay. Ciao, guys. Take care.
Ciao, Daniel.
Ciao. See you later.
Ciao.
Thank
See
you
you later. Ciao, ciao.
Okay, so I think we can reconvene directly for
That's
the
it.
Q&A, right? In
Right.
1 hour and 45 or
Yep.
whatever. Okay.
Yeah, at 7. You are
Okay.
doing it, Enrico, right?
Sorry?
You are doing it, right? You said.
Yes. Yeah.